So I'm a part of the Advanced Visualization Lab at the NCSA. We do scientific data. We do visual treatments of that, normally in sort of a cinematic style, so that it can be shared in documentaries. And we do all kinds of releases where we'll do like digital dome movies for planetaria, and we'll do IMAX 3D kinds of stuff. Just like Nova documentaries, all kinds of things. And we also have a lot of projects that we do visual work with artists. So we've done a lot of stuff at the Krannert Center, and we do different kinds of technology and performance stuff as well. But I'm mostly going to talk about the space visualization. We do a lot of climate and outer space kind of stuff.
Where does the money come from for these visualization adventures?
It depends a lot on the projects, but especially the big productions are generally already funded by a company that's producing the film, and they come to us and they want specific sequences. And we have relationships with scientists so that we can use their data and we can reuse their data, and so we have like the world's most advanced visual model of the Milky Way, and people keep coming to us and they're like, we want your Milky Way in our film, and we'll do different treatments of color and density and camera flight so that it doesn't necessarily look the same every time, but
so Star Wars 7?
Exactly. That's in the pipe, definitely. Hopefully.
That's not a joke, right?
If only.
Isn't that a documentary coming out?
It's a true story. It's a true story. I think Star Wars happened a long, long time ago, so the sequel could be here. Yeah.
And it's in a galaxy far away, so it shouldn't be the Milky Way galaxy.
Andromeda, probably.
No, that's a galaxy close by.
Oh, a far, far away galaxy. I can't think of any.
And how does it work with the MSTE for the original mission of the center?
Yeah, so it sort of fits into the education and outreach part of it. We are kind of the part of the NCSA that actually gets seen. So we'll take the data that's coming off the supercomputer frequently and turn it into really nice visuals or whatever. And that works for us in terms of like, we can get notoriety at film festivals. We can get releases into productions that are in movies or domes or whatever. We can even just release things online. We did a project with NASA where they want to launch a telescope called the James Webb, which you guys may have heard about. And they wanted sequences that explain what the value of the telescope is. And so we worked with them, and those are all online now. So that then helps the center to bring in more researchers and helps the center to bring in more notoriety, I guess. At least that's my take on it. You might get a different answer from my boss, but that's how I understand it. And then, like I said, we also do a lot of work with campus. We do a lot of collaboration kinds of stuff we have like a really strong climate science team, and so we work with them a lot. Or like at Krannert. So some of our funding does come through the university, and that's sort of what we do there. So shall I? Okay, here we go. So now that I've already told you this, I'll do it again. So these are some of the films that we've worked on recently. Hubble 3D and Space Junk were both IMAX films. Dynamic Earth is our most recent dome show, which I think is showing at the Smithsonian now. And Tree of Life was this Oscar-nominated film that really polarized people. A lot of people loved it, a lot of people hated it. But it was really pretty, and we contributed to the prettiness of it. So these are some images from the Hubble movie that we did. And this is just sort of to give you an idea of the different kinds of data that we work with. The Orion Nebula was given to us as an 18,000 pixel by 18,000 pixel image of a nebula, which, if you don't work with images a lot, that's huge. That's really, really big. And so we laid that onto a plane in 3D space and then started carving out the plane based on a lot of scientific research papers about these sort of 4 big stars that you might be able to see. Do I have a pointer here? No. Well, anyway, there's 4 bright spots in that nebula, and they blow really strong stellar winds, which push out this cavity in the nebula. And so that's sort of something that we had to kind of help us figure out how to shape it. And then after we had sort of created a terrain and created a camera path through it, then we were able to render it really nicely. The sort of blue stuff in the background, that was a supercomputer simulation of dark matter, and it's the beginning of the universe where a bunch of matter it gets denser in dense places and sparser in sparse places, and basically you start to get these long strands throughout the universe that turn into galaxies, and if you got in really close, you could see actual galaxies forming and stars inside those. And then M87, that's a statistical simulation. So based on what we know about how many of one kind of star, how many of another kind of star exist inside the M87 elliptical galaxy, which is something that we can observe with the telescope, but not in enough detail to fly into it like we did in that movie. So this is a couple other things that we did for Tree of Life. We did supernovae, which were a supercomputer simulation. We did that Milky Way model that I had mentioned. So here's actually, this is a video of that same cosmic web simulation that I was talking about. We did 2 sequences for space junk. We did the cosmic web, and then we did colliding galaxies, which are sort of 2 different scales of similar phenomena. So you can see sort of far out how a bunch of galaxies interact, and then we get in close to see just these 2. And this is sort of a simulation that was created to show what might happen if or when the Milky Way and Andromeda will collide, for example.
And the time scales are like billions of years there, right?
Yes. It definitely wouldn't happen that fast.
You know?
Can I ask a very elementary question? Tell me the difference between visualization and animation.
Again, this is going to be my take on it, and a lot of people will give you different answers. But visualization is taking something that already exists and making it more communicative, whereas animation is fabricating something. There are certain elements of animation that we use in visualization, but we also we're starting with a lot. So, like in this cosmic web simulation, there is an enormous amount of detail that we never had to create because it already existed in the data. So from that perspective, there are a lot of animation techniques that our team really doesn't use at all in terms of just creating stuff from scratch that's not necessarily accurate. And I would say in an animation studio situation, it would be a weakness, but since we're given all of this data, our strengths are in making things look nice, and so we're good at the rendering, we're good at the camera flights, we're good at the simulations. Sometimes we have to create our own simulations if there's no supercomputer data to use.
The key thing is that visualizations have data.
True, yes. I mean, yes. So technically I'm talking scientific visualization, and there's other kinds of visualization, but I think for the most part, that's a good way to think about it. So then this is a shot from this new Dome show that we released. It was narrated by Liam Neeson. It got a lot of attention. But we got 5 terabytes of data from NCAR, which is the National Center for Atmospheric Research. And it's apparently even still the most advanced supercomputer simulation that's ever been run on a hurricane. And they were actually running this in a race with the actual Hurricane Katrina because everyone was trying to figure out where the hurricane was going to go and what it was going to damage and all that. And this ended up being the one that was the most correct. So we asked them to rerun the simulation at a higher temporal resolution so that we would have data steps for every frame of this movie. And then we added this treatment to it. And one of the things that the scientists said was that you want to point out these hot towers, which are these big, powerful thunderstorms forming at the edge of the hurricane, because they're well known in the scientific community to really feed hurricanes. And that's the reason that hurricanes start to die out over land, is they don't have these hot towers forming. So that was something that we highlighted with those yellow arrows. So anyway, why are we at a supercomputing center? There are two really important parts of what we do that use the supercomputer. One is the data that we're reading into our scenes to create the visuals in the first place. And the other is the rendering. The imagery gets to be really big, especially when we're dealing with IMAX resolution, or if we do stereo 3D, you have to double the resolution immediately because you're doing two images. And dome renders are actually some of the highest resolution images that we do, and I found that surprising, but it turns out that it actually makes a lot of sense, because there's not only a screen in front of you, but there's kind of like a second screen behind you, is the way to think about it. So I was thinking when I was making this slideshow about explaining how this whole like complex pipeline graphic works, but it's sort of unnecessarily complicated. It's really kind of a 4-step process that just has some iteration. The first step is we bring in the data, and we have to sort of format, because every scientist has their own sort of way of writing data, and every science field has their own way of writing data, and to us it's all the same, but we need to read it into a format that we can use. So first we import the data in a way that we can use it. Second, we start exploring the data. We look around it in 3D like pre-visualization tools to figure out what's in there. And then we can start designing the scene, and then once we've put in all of our design elements, we render it out. And sometimes we can do that on our own dedicated cluster, and sometimes our dedicated cluster isn't enough, so we also get time on the supercomputer. But we try not to take too much time from the actual scientists. So this is the team. We're not very big, but we have a lot of multiple specialities. But this is, I sort of just put the roles that we're sort of most comfortable in. But obviously, based on the project, since we are a small team, we have to kind of switch around a lot. So now I'm going to switch over to the motivation, which is going to kind of get back to the question you asked. Why does the advanced visualization do what it does? And it's sort of these three things: discovery, promotion, and education. The tornado image that I actually have up in the top left is a really good example of how visualization is actually a tool for scientists too. And it's not as frequent for a cinematic treatment of the data to be a discovery tool, but it does happen sometimes. And when we were creating that sequence, it was based on a real tornado that happened in North Dakota. And then the data that came out of that real tornado seeded a supercomputer simulation of a tornado. And the simulation, once we visualized it, showed that there was actually an anticyclone that formed. It was a second tornado that kind of came, in our visualization, it comes into the foreground. I don't know if I have that in here. But when the scientists saw the animation, they were really surprised because they didn't remember there being two tornadoes on the ground. But then when they started scanning through their numbers, they actually did notice that it was there. So it's the common, a picture's worth 1,000 words kind of thing. Looking at numbers is one thing, but looking at a picture with 3D data, you can represent X, Y, and Z as three different variables. You can represent color as a variable. You can represent motion as a variable. And in the tornado sequence, there's all kinds of different shapes also flying around the scene that explain stuff. So that's sort of a long-winded way to talk about something that we don't do that much, but promotion and education are both very important to us, and education especially, which is why we get involved in a lot of documentary programs, and why actually a lot of people seek us out, because they're looking for something accurate. That's actually how we got involved with the Terrence Malick Tree of Life thing, was Terrence was like, hey, I'd really like to have something that actually represents the evolution of the universe and isn't just Hollywood bullshit. So that's sort of where we specialize. So aside from sort of having fidelity of the data, we're also creating images that really look a lot nicer than the artistic equivalents. So I found some sort of comparisons online here, but a lot of scientific theorizing requires, especially for communicating it to people who aren't in the field, they collaborate with artists a lot to create things. I mean, like dinosaur pictures, you see those all over museums, right? And no one actually has a photograph of a dinosaur, so it's all kind of artistic interpretation. So what we're doing is we're sort of doing we're creating some kind of data to create the image rather than just doing it from scratch and from imagination. Oh, this might not be the most recent copy of this because it's missing an image. But anyway, so this is sort of a couple images of the data before it comes in, or before it's in the scene. One of the that's interesting. Well, anyway, so just for examples here, the image on the left is an electron micrograph of the human papillomavirus. The one on the right is the Hubble Ultra Deep Field image, which, if you're unfamiliar with it, they pointed the Hubble telescope at a tiny black patch of sky and just let it sit there and collect photons from much farther back in the universe's history, and actually got these really nicely resolved images of galaxies from long, long ago. Like the narration is like before the Earth existed. And what we did was we wrote custom software that went and found like an individual galaxy, and then clipped out a small image of, like, just sort of a postage stamp image of that galaxy. And then we layered all those postage stamp images in depth so that we had 3D data that we could fly around. Next. No. So then after we've sort of pulled in the data, we have to simplify and clean the data and make it something that's usable. Alex Betts, who's a member of our group, he actually resides up at the Electronic Visualization Lab in Chicago. He has written a plugin for Maya. Maya is 3D animation software. It's predominantly what we use aside from in-house tools. This plugin will read all kinds of data, format it, and then spit it into Maya, and it can do all these. There's a list here of all the kinds of features that it has written into it.
When you say you clean the data, how do you determine what is the noise that you want to clean out?
Sometimes it's really obvious. Like you'll have like a you'll have a 3D grid, and you'll see the edges of a 3D grid cell because things are moving through it, and it fills in a corner where it's supposed to be a smooth object. But other times we actually have to talk with the scientists or the data science, like the people creating the simulations. So like this, this protoplanetary disk, the red ring, the data actually had a halo above it, and it took a lot of exploration to sort of figure out that halo was even there, but we really like pushing and stretching and figuring out what all is in the data. And we found this halo, and we talked to the scientist, and he's like, "Oh, hide that. That's a data artifact. It's something I use to feed the simulation, but it's not actually part of the simulation." So that's sort of the two ways I think that we do that. Okay, so there's a couple other tools we have. Matt Hall, who used to be in the group, he's now in Arizona. He wrote IVRView, which is sort of a real-time application, and Amore, which is the final rendering application, to deal with adaptive mesh refinement data, which, if anyone here is an astronomer, you're probably familiar with it. but adaptive mesh refinement is basically volume data, so like 3D grids. But instead of each grid cell being the same size, you only have grid cells where there's actual detail, and it saves you a ton of data space. But the problem is that none of the real graphic software out there actually works with adaptive mesh refinement data, so we've written our own. So PartyView is a real-time particle rendering piece of software, and so that allows us to sort of explore data. We can either take geometric meshes and turn them into clouds of vertices and fly around those vertices, or like a lot of times we'll be doing outer space stuff, and so it makes sense to have little dots in a black void because they're stars or they're galaxies or whatever. And then, of course, we have all the manual methods where we'll like go in and into the numbers and start deleting stuff that shouldn't be there, or we'll interpolate and create extra data steps. And we use image compositing a lot to sort of help us where the data can't. So that's the halo I was talking about. So actually, we have a render of that. And yeah, the other image then sort of has the blockiness. So there's some things that are visually obvious. There are some things that you think, oh, hey, that might be important to highlight. Maybe we should draw out this halo and show people that there's a halo there, but it turns out not. So then in creating the scenes, does everyone here know about the cave? Does no one here know about the cave? Who's familiar with the cave? Not? Okay. So the cave was a virtual reality environment that was at the Beckman years ago. Or it's actually still at the Beckman in case anyone's interested in visiting it. It's at the simulation laboratory in the South Farms. But the cave was this 3-wall room with a floor, and it all had stereo projection, and it had head tracking, and so it was a really good scientific environment for scientists to explore their data. And there was like a little wand that they could use to control things, and it was very progressive, and everyone wanted it back in the day. One of the applications that was written for it was called Virtual Director, which is sort of the application I was describing where you can fly through stuff. At some point, the NCSA split out from the Beckman and started focusing on data problems where Beckman was focusing on science problems. But Virtual Director sort of came with us, and so when we got this, we have a 4K stereo display in our laboratory, and we rewrote Virtual Director basically to work with that. And so what Virtual Director is for us is a pre-visualization environment where we can both work with scientists to look at their data in real time. We can fly around it. It's stereo 3D. We have a 6 degrees of freedom tool called the Space Pilot, I guess. It's just this little puck that you can sort of fly around the environment in. And we have our little like press photo there of everyone pointing at things in 3D. But one other really important feature of it is that it has, it's collaborative, it's networked. So we actually, I think it was first developed before I was part of the group, but it was developed with the American Museum of Natural History in New York, and it was built with that PartyView piece of software I was talking about so that they could have interactive shows of the night sky in their planetarium dome in New York, and we were able to work with New York from our visualization lab with floating avatars. So basically, like I think they're represented as like a big floating smiley face, like the Jack in the Box character kind of, and we're represented as something else. I don't know, but oh yeah, actually no, you can see it right there. This guy, that's the avatar they would see, and so you would know where each other's cameras were, and you would know how big you were, and you would know what was important to see and that kind of thing. So that's something that we're continuing to develop. Like we're working with our second dome production with the Adler Planetarium right now, and they actually have a dome so we're working on it for their big dome, but they have a small dome, which is like 15 feet in diameter. But there's a huge difference between seeing something on a flat rectangular screen and seeing it in a dome. And so what we're doing is we're using like our expert visualization artists down here to create camera pads, and then the people in the mini dome up in Chicago are watching it and saying, oh, like that object got clipped off by the dome, or you're seeing something that you really don't think you're seeing because it's behind you, or something like that. So it ends up being a really useful piece of software. And then, so I guess I just mentioned a few of the pieces of software that plug in objects into this virtual director software. So we can do VMaya, which just stands for Virtual Maya, and it basically shows any kind of geometric light texture objects that you can create in the Maya software. We have PartyView, which can do vertex clouds, point clouds. It does these long lines called trajectories. And then the adaptive mesh refinement, we actually set it up in PartyView with just 8 vertices to represent a box that shows you the resolution of the fluid that you're flying in, or sorry, the volume that you're flying in. But it's all sort of set up so that you can understand what you're looking at without having to render it in the sort of final format, and you can do it faster. So after we pre-visualize it, then we design it, and we use a lot of fluid effects, volume effects, particles, isosurface stuff, which there are examples of here. And then the other thing we do a lot of is, my boss, Donna, who's in charge of the group, she calls them visiphores. They're visual metaphors. It's a very clever contraction. But the arrows here are sort of this common glyph that we use to show volume data, vector field kind of stuff. Basically, if we get a 3D vector field, we can release particles into that vector field and watch where they go, and then trace a tube that is the path of the particle. And that was a glyph that we created to sort of demonstrate the tornado vector field. And then we found out that it was actually really very communicative, and so then we started placing it into all kinds of other scenes, and you could even see it in that hurricane clip that I played. So then we sort of, that's, after we get all that done and we've created the data and we've made the data look really nice, often the data is not the kind of resolution that we want for a really high resolution scene like IMAX films would. So we have to start adding in procedural noise and high resolution kinds of imagery to really improve the look of it, so that it's not only communicating the data, but it's also looking sort of photorealistic so that people stay immersed in the story. And then the final step is to run it through a ray tracer or a renderer. And so we use Mental Ray a lot, which is just the built-in ray tracer in Maya. We use Pixar's RenderMan. We use something that was written, well, so Amore and Star Renderer were both written in-house, and they're both good at handling massive data sets much more efficiently than the commercial software is. So Star Renderer does particle data a lot better than basically anything else.
So where does one acquire these pieces of software, and how long does it take to learn them? There are 3 programs. What's involved in becoming facile with using them?
There's all kinds of software, and like I'm only now becoming familiar with just how much software there is, because in the effects industry you've got things that will do just smoke, and you've got things that will do just water, and like they're all plugged into these, like it's just this big web of software. But Maya specifically has basically anything you could ever want to do. It's just not necessarily the best. So these pieces of software here are the renderers, and you can set them up to all sort of read the same data that's been created in Maya, or created in one of these in an interactive environment, and then you run that data through a renderer. And learning renderers, I feel like, is a lot of understanding how light moves, how eyes work, and that kind of stuff, and then knowing what variables exist in the software and trying to match up what you know about the science of vision with the options that are given to you. And then it's just trial and error. You run an image, it looks wrong. You run another image with new settings, it looks wrong. And you do that 10,000 times until you get something that looks right. And
so it's an artistic adventure.
Yeah.
As much as that.
Right, yeah, it definitely, it eventually gets to the point where it's all just sort of visual feedback and determining whether it looks the way that it should or not. And there are certain things that work sort of better out of the box and things that don't. Since Star Renderer and Amore, which were both written at the NCSA, since they're such specialized software, they tend to work pretty well just right out of the box. But Star Renderer basically only does particles, which are XYZ position in space, and then it'll just spit out a dot at a certain size at a certain brightness. And if you want the dot to do anything special, you start to sort of stretch its abilities.
How much is it an individual effort and how much a collective? Like where are the points where you say to somebody else, how does that look?
Oh God, I do it all the time. Yeah, so that's the thing, right, is that like, I'll be sitting there like trying to create something completely, so like we did a scene of a Venusian volcano, and I was creating a smoke plume for the volcano because we wanted a supercomputer simulation, but we talked to Susan Kiefer, who I think is the resident volcanologist at the U of I, and she was like, you're not going to find what you're looking for. It doesn't exist. No one's run that. So it fell to us to sort of simulate our own just artistically based on what we knew about the science. And so, you know, I sat down at my computer and I started using Maya's tools to sort of simulate this plume. And I sort of very quickly found out that there were limitations to it, and sort of jumping ahead. So I spent a couple of months developing this plume and created it. The simulation looked great. I played it back at 30 frames a second, and it was like 3 times too fast, and that made it look really small, and it made it look like it was like almost coming off the end of a cigarette rather than being like a volcano plume. So then I had to go back to the data guys, and I had to be like, here, I created this simulation. Can you slow this down by 3? And so then they had to like mess with the numbers and create interpolated frames and that kind of thing. And then they passed it back to me, and I was able to then render it. But then Bob, who's another member of our group, is the one that was compositing all of the layers together of the surface of Venus and the cloud layers of Venus and the plume. And so then I had to go talk with him about how that layer was going to interact in his composite scene versus how it was interacting in my 3D scene. And so everything's really very interconnected, and half the time I don't know what I'm doing, so I need someone to explain it. But yeah, does that sort of answer your question?
Yes, it does.
Okay.
And can I throw another one? What's the
Sure.
best preparation if you talk to a kid who said, I want to do what you're doing?
Oh God.
What would you tell them to?
I have a litany of pieces of software that they should play with. Maya is sort of the industry standard can do everything piece of software. It has a really high learning curve, but there's a lot of documentation in it, and it's fantastic. It's so well written. But I guess the way that I learned it, and it's the way I would recommend, is taking some kind of class where you're just introduced to the very basic concepts, where you're taught how to navigate in the software, where you're taught what certain keywords mean. And then you can start exploring it on your own. Maya has I think there's like Autodesk University, I think is what it's called, and you can get all their software for free if you're a student. There's also Blender, which is the open source alternative. I used to not recommend it because it was so, the interface was so completely different from Maya that you would have a hard time like just picking one up after the other. But I've been told since I was last playing with it that there's actually plugins that make it look exactly like Maya. So now I think it's probably just as good. And it's open source, so it's completely free, and you can even hack the code if you want. I feel like there's another important thing. Oh yeah, so then if people really want to get into like the scientific part of it, all of these other pieces of software that I made vague reference to before, there's something called Houdini, which does volume kinds of data. There's something called RealFlow, which does particles. They do water fantastically. Like basically any movie you see with a water effect is done with RealFlow. They all have free trials. And so I would highly recommend toying with all of the free trials out there. So, yes. I'm sitting here thinking there's probably like something that's a little bit more kid-friendly too. But, oh yeah, sorry, go ahead.
In your group, is there any science educator? Because
we've had educators come and go. Yeah, sorry, finish your question, go ahead.
I feel like you are very beautifully communicating with data, but I don't see how to like teach with that data or how to use that visualization. So
yeah, so that's a really good question. It's something that we're always sort of conscious of. We have had educators as part of our group. The most recent member has left for New York a few months ago. But the other side of that is that we're constantly in communication with scientists and then the production team. Because remember, most of these shows aren't actually our shows. They're being produced by someone else that we're contributing to. And so like right now we're working with the Adler, and the Adler has their own education staff. And so the entire film has been written with a script that's very focused on how do you properly communicate things visually, how do you properly communicate them through the narrative. The last Adler show that we worked on, it actually was an interesting experiment because it was a sci-fi story. The narrative was about an alien traveling through the universe and looking at sort of outer space phenomena. And the feedback that people got, or that they got in their education research was that visually it communicated the science better than they ever could have hoped. And like people who spoke a different language understood what was going on, and people that had never, even heard about a protoplanetary disk suddenly knew what a protoplanetary disk was supposed to do. But a lot of the people that were informed were sort of insulted that it was a sci-fi story instead of a science narrative, because they felt like it wasn't explaining all the information that it could have been doing. And so now they're sort of flipping back, and they've gotten... So I think the writer for the previous show was Nick Sagan, Carl Sagan's son, which was kind of funny because it was science fiction and not science. But this new one now, they've actually gotten a really well-renowned science writer, educator person to write the script for the new movie. So that's sort of a long roundabout way of telling you that yes, it's a very big concern that you're not just creating something for the sake of creating it, but that you're actually creating it with an education goal in mind.
Thank you.
Yeah. Any other questions?
Well, different educators will have very different audiences in mind. So what you would be helped by somebody who's working with public school children is not the same as what somebody's working with the people who want to work with the Adler contracting and funding people and so on.
Yeah.
So lots of variants.
It's true. It's sort of a tough battle, especially because a budget to create a big like digital dome film is so huge that it's not something that you can just say like we'll create a targeted audience, sort of we'll create a film for them and a film for them and a film for them. One of the things that's really cool about what we can do is since we own the data, or at least we can use the data freely. I don't know who owns the data, but we can recreate the same kinds of stuff in different contexts. So we can create something that speaks to school children and something that speaks to the astronomy crowd and something that speaks to, you know, your sort of early expert college student or something. So that, and even the rendered out sequences, after we've created the renders, we can then go and reuse those renders in certain situations too. So there's a couple more slides. I'll just talk about our display environments. Then we have this high resolution stereo 3D environment, and that's actually a picture of the lab that I keep referring to. And then we also do digital domes, and we actually render those as a series of rectangular images, which we then place in 3D space as if they were a dome, and we project rays, and we average together the pixels that they hit, and that's how we create our dome images. And actually, one thing that a lot of people don't really realize is that the dome image isn't just a flat circle. It's actually it's actually built in 3 dimensions. So when you look to your left, you're actually seeing things that are to your left and not things that are just above you on the circle. So it's a very immersive environment, almost as much as the sort of stereo glasses 3D is. And these are just a few of the productions we've worked on recently with Denver, New York, California Academy, and Adler. And then we also have this Panorama Display, which is 3 HD screens stitched together. And it's, yet again, another immersive environment. It's got this peripheral thing. It's not just a long rectangle. It's actually got cameras at different angles, and so you get this sort of surrounding feeling. And we use this a lot more for the sort of the performance art stuff that we do. Okay, so there are the credits for the things that I didn't mention in the slideshow. Credits are very important in what we do, so people don't feel insulted or sue.
Little did you know you are personally liable.
Yeah. Oh, crap. Yeah, they wouldn't get much out of me.
Thank you so much.
No problem. So, if you have any questions.
Yes, you're not ready to quit. Let's go back to George's first question about editing and your answer, which was quite satisfactory, or better than that. This is a very complex matter as to whether or not it should be cleaner or messier, as you well know. I mean, you told us that. And to take out the halo or to do anything, just because one person says it's an artifact or I don't want it or something like that, isn't necessarily the best visualization or scientific meaning. You made a nice distinction between visualization and scientific work before, to the extent of moving out of Beckman or whatever.
Yeah, with the cave and the virtual directory, yeah.
But the scientists are hugely into visualization, advocacy of a perspective. And
that's absolutely true.
Visualization people don't want to get very far from what is considered to be scientifically respectable.
Mm-hmm. So yeah, in a lot of situations, our hands are sort of tied when we're working with a specific scientist who's run a specific data set. Actually, so that protoplanetary disk that I was talking about is a really good example. Yeah, this red guy here. So he he was created with the question, how do planets form from these disks that we know exist because we've taken pictures of them in the Orion Nebula, for example. But how do these big rings of gas and dust actually turn into planets? And there are two really popular theories, and this only simulates one of them. And I think actually the predominant theory is that both of the theories are correct and in different situations. But when we created this animation for NASA, we only advocated that one perspective. We only talked about how, oh, this shows how planets are forming. Well, it's not the only way planets might be forming, or it may be completely wrong. It may be that the only way that planets form is the other way. So in that sort of regard, our hands are tied a lot in terms of what perspective we're showing. On the other hand, a lot of times we'll be working with artists who are, writing a script that is supposed to tell a narrative, and more often than not, they will have done their research and they'll know all the different theories, and they'll actually write a script that says this may have happened or this may have happened, or they'll even ask us to take data that we have that they know conveys a certain perspective, and then they'll ask us to use our artistic tools to either change or edit the data to contribute to the narrative of this is only one perspective, or this is even the wrong perspective. So from the artistic side of our group, we're able to change the perspective, absolutely. You're right. And sort of our lean is toward scientific fidelity. We want to sort of respect the science community as much as we can. But obviously, like, depending on who's paying for it, who's giving us the data, we sometimes have to sort of go with something that we're not thrilled about. But obviously, we never lie.
Science depends upon argument. Science depends upon having adversary relationships about explanation and the like. And if you go too far into persuading everybody that that's the right one, whether intention or not, you lower the scientific
discourse. Yeah.
discourse.
Yeah.
So, I mean, I'm thinking of whether you should be on the stand for being charged with upsetting science, but all teachers are in the same boat of representing things too simply so that everybody can learn.
Well, and like, actually, it just occurred to me when you were saying that, I actually remember talking with Adler, and part of that science fiction story I was talking about, one of the motivations to having that was that they didn't want to give answers to unanswered questions. They wanted to show things as possible, they wanted to show things as plausible, but they didn't want to say for certain, this is certainly the answer. So when we were working with them, there was very much a motivation of keep it open-ended. Just inspire questions rather than give answers, I guess. So, but it depends on who we're working with, definitely. The dome shows are actually much more scientific, I feel like, than the produced ones like Tree of Life and the IMAX film, because they rely on making a profit, whereas planetarium audiences are already interested in science, and they're sort of a captive audience. They're going to go see the movie that's at the planetarium. So they don't really have to worry about their box office so much. So. That's the best I can do to address that concern, though.
I think in the realm of education, though, like what you're talking about the nature of science. So I think it should be explicitly stated that this is a model, and all models are false. Some are useful, like this. So it just needs to be explicitly stated in that.
Not false, are just models.
But then sometimes you can give an option, another alternative. Instead of, if we take all the blue lines out of this, I mean taking something out of the picture, sure. But if we put the green lines in with more visualization, it does change something, such as the noxious gases involved, or such as the danger of implosion of buildings.
Well, and there was something that I was expecting to be in this slideshow that wasn't, and if I can pull that up really quick. It does a really good job explaining how data is yeah, that guy right there. How data is subjective. So these are 3 pictures from the same camera angle, from the same time step, of the same database of numbers, but we've chosen to emphasize different things in it, right? And they imply all kinds of educational points, right? Like if you're looking at something in space, is it going to be blue or yellow, right? Is it going to be bright or dim? Is it going to, even just visually, and that's not even including sort of the dynamics of this simulation. And like one thing that anyone in space imagery will tell you is that everything you're looking at is faked, because even if the shapes are correct, that like pinkish nebula, that was like that guy there, that would be green to the human eye. It would all be a very solid green. But they decided to shift the image in the color space so that you get a broader range of colors, and so that they would sort of be visually pleasing. But at the same time, that almost communicates more, because if you are able to sort of draw a stronger contrast between pinks and purples, then you know that there are more features happening inside those clouds than you would have seen with your human eyes. So we treat the camera as a special kind of eyeball, I guess.
I'm just curious though, what's the true image, and what the idea of lying with images? You don't know how to answer that really with this.
It's true.
And
I think a lot of the people that we work with are very conscious of it, and they make a deliberate choice whether to do it or not. It's always part of the production process. Is like, how much of the real thing are we going to show? And that's something that we were just working on yesterday. We had someone down from Adler working with us on pre-visualizing a scene, and we had a protoplanetary disk. That same protoplanetary disk, if you look closely at it, it actually has two white blobs forming, and those are planets. And those planets are orders of magnitude farther from their center sun, their center star, than Jupiter would be. And our sequence is supposed to show this transition from a nebula to a protoplanetary disk down to Jupiter, because we're seeing the formation of the solar system. And the question was, should we put Jupiter lined up with one of those blobs, which is actually orders of magnitude larger and farther than Jupiter, so that people can understand the connection between forming planets and Jupiter being a gas giant? Or should we create it precisely accurate to the point where actually it's sort of a donut shape, and there's a donut hole, and Jupiter would actually be sitting inside the donut hole of that simulation. And so we don't know if we're going to use the simulation as sort of we're going to just pretend that it was Jupiter scale, or if we're going to say this is actually the solar system and these are just big old planets that don't exist in our solar system for some reason. So it's always an interesting sort of battle between absolutely factual and communicative, I guess.
Do the raw images ever appear in the popular press of, say, I think you were showing or you were talking about these telescopic images where they just sit and let the photon.
Right, of the Hubble Ultra Deep Field.
Just yes, no.
Right.
Pixels, right, black and white, and so then they get colorized.
So okay,
they go through filters.
Yes,
yeah. So I sort of glazed over part of the process, which is so I keep talking about how we work with the scientists. In the case of the Hubble movie, we worked with the Space Telescope Science Institute in Baltimore, and they are the specific site that works with the Hubble telescope, and every image that the Hubble telescope takes, they process before it ever gets released to the public. I don't know if they process it before they even release it to scientists. Probably not. But anything that you've ever seen in the press taken from the Hubble has gone through their office. So for instance, I was talking to Inga last week, and she was talking about how the Hubble telescope for the deep field had actually not snapped one photo of that dark spot in the sky because it wouldn't have been able to stay in the same spot long enough. But it actually did several passes where it kept snapping that same spot of sky. And then those many passes that had just a few lightly colored pixels got added together by the Space Telescope Science Institute until you actually saw all of the photons start to sort of trace out these galaxies. And that one, aside from the layering, the addition process had very little image processing on it. That being compared to against like the Orion Nebula, which was very heavily processed, and they were shifting colors all over the place. And my understanding is that the reason that they shifted the colors was to show a large range of colors to as many human eyes as possible, because like everyone's eyes are different and they can all see different color ranges and stuff, and so they were trying to make it as communicative as possible. And the other thing is that I say that it appears green to the human eye, but it doesn't appear green to the Hubble's eye. Hubble doesn't actually snap images that are accurate to human biology. So the colors are already sort of remapped when they get them, and then they just try and stretch them and draw out details so that they mean something.
And a lot of the detail you see in astronomy is actually outside of the visible spectrum. So like the James Webb Space Telescope, correct me if I'm wrong, it's all far infrared. There's nothing.
Yeah, they're not even doing visible light.
Yeah, it's all
absolutely
infrared. So if you want to visualize anything, you're going to apply some false color to it.
Yeah,
and
in fact, a lot of the telescopes that are even out there right now do an infrared shot, an ultraviolet shot, and a visible light shot. And the Hubble movie that we made, they did this thing in 3D. This was the Space Telescope Science Institute that did those sequences, but they actually took the same nebula and they showed you the visible light and then the infrared take of the same photograph, and they were perfectly lined up. And the infrared actually is sort of an X-ray. You can see into a big cloud, whereas the visible light, like, you only see as far as the cloud starts. And so it was interesting to just sort of have this crossfade from like the pretty like pinks and purples to sort of this greenish thing with bright like red and blue stars nestled inside.
Oh, so now I think I've got it. It's not a matter of true or false. It's a matter of accuracy of translation.
Right.
You're translating.
Right. Yeah, because I guess the truest, I think sort of the perspective of image scientists is that the truest image you could see would be what you would see with your own human eye. But that's very rarely the best image, because human eyes are extremely limited.
And another thing to think about is, for the tornado movie, it didn't have little ribbons of yellow. It's the same thing. It's just we think that it's, because it looks like sort of what you might see through it actually doesn't look anything like you would see through a telescope. Because if you go out with a telescope, everything's white. Because the receptors that you're using, your low light receptors, don't have color, can't really distinguish color. So
I presume those were indicating air movement.
Right, but they're an indicator. That's what I'm saying, is that it's part of the visualization process to provide other bits of color to highlight things that they want you to look at, to have things showing numbers that you can't see with your eyes. And if you think about it, that's what the astronomy stuff is too. They're overlaying X-ray, UV, ultraviolet, visible, and often there'll be phenomena that are very distinguished in a small range, like the bright green you were talking about. Mm-hmm. There might be several different bands in the green to the human eye that all mean different emission spectra from a certain kind of star, indicating some different phenomena. And they want to color those differently because they don't want it to look like it's the same thing. They don't want, a young, large star to look like an old, cool star when they're both giving off, similar wavelengths of light, but slightly different.
True. Oh, go ahead, yeah.
So you incorporate more data like speed or things like that when you were doing the tornado. So it's not just visual, it's also other types of data?
Right. So we also do a lot of remapping of data, where we'll take a variable like speed, which is sort of an abstract thing, you can't see speed, and then we'll map it to something like time. So each, as you step through time, you see the difference, which is what speed is. But we also do some, like in the tornado, for instance, or even in the hurricane that was at the beginning of this, The tubes that you see inside this video are colored based on vertical velocity, so how quickly they're rising or falling. Blue means that it's going down toward the surface of the planet, and yellow means that it's rising. And the bright yellow tubes were showing those hot towers that I was talking about. It's kind of working.
Yeah, it's real choppy.
Oh, because I have two of these things open at the same time. But yeah, so we're also using color to show velocity. So yeah, we can swap variables all we want, and as long as we communicate what those mean, then we're not necessarily telling a lie. We're just not showing something that's photorealistic or eye-realistic, which is even worse.
So you told how to start a youth into this field. Are there services or offices or labs on this campus that are at the youth stage rather than at the more mature stage you've been showing us of your work?
That is an excellent question. So sort of what I've been hearing is that a lot of schools now are teaching like CAD, computer-aided design, at a lower level, where like I think my school was being really progressive in teaching it freshman year of high school. I've heard that it's now being offered in a lot of junior highs and stuff. And that's essentially the same kind of like mentality. It's using the same sort of set of tools. And so once you get to sort of the user interface level, it ends up being different depending on what your application is, whether it's animation or CAD or whatever. But it's certainly a good start. I mean, like, I knew that there were summer camps that were doing, like, you know, elementary kids can do 2 weeks of something at the community college, for example. And I think that I saw that in Parkland's course catalog, but I can't guarantee that.
I think Saturday Art School has a little bit of that in its high school program.
Okay.
I think.
Okay.
I saw that when I was signing my daughter up.
Okay. Yeah, no, that'd actually be cool to know, because I get asked that question a lot, just by the people that, like, they'll do tours at the NCSA and they'll take kids through, like, elementary school kids are visiting all the time, and every once in a while they'll get a kid that's like, I want to do exactly that. How do I do exactly that? And it's like, okay, well, first you got to know this, so you have to learn that, so you have to learn that. And there's like this whole...
Well, I really like your answer that here's a bunch of programs, you know, dig in and see.
Go play.
I mean go play sounds like a really
so
advice as opposed to take algebra.
So I actually have a cousin that talked to me about this very thing over the summer. He's maybe a sophomore in high school or something, and he just wanted to make modifications to, like, not Quake, but, you know, Team Fortress or something, one of these first-person shooters.
Yeah.
And that ended up into him trying to learn 3D Studio Max and doing his own geometry and mapping bitmaps onto it and things like that. So mods for video games is probably a way to do this. It's a sort of it's a way to get someone from playing a lot of first-person video games to maybe designing their own levels for it.
And there was a game engine that was used for Team Fortress, which has open sourced. Do you know what I'm talking about?
Yeah, that's the one he was using. I don't know the
name. Oh, is that
of it.
okay? Yeah, I forgot. Yeah, so
it was for Team Fortress 2, and basically you could use the engine, create your own worlds, create your own monsters, but you'd have to create the geometry, the animations, skin them with, and it's not exactly the same as this, but the big learning curve is just, I mean, if you can create a cube with a sphere on top of it, you know, that's like a 2-day thing in a lot of these CAD programs to get to the point where you can do that. I mean, so,
yeah,
you know, once you get to that, you know, once you're doing video games, doing a different set of plugins and stuff is a
And that actually sort of gets back to what I was sort of in the middle of a long paragraph of trying to say. It was that There are a lot of different pieces of software that specialize in different kinds of things, and one sort of set was those renderers. Another set is simulation software, which is really relevant to scientific visualization and not much to, it's not very relevant at all to like video game, not really to video games or even necessarily like character movies. But there's like, so RealFlow is this industry standard piece of software that basically in the course of like 3 button clicks, you create photorealistic water and it behaves physically accurately. So like, I think it would be really interesting to see a young kid pick up that piece of software and just click 3 buttons and all of a sudden have something that works right in front of them. Like they don't have to like do a ton of work just to get to the beginning stage, right? They've got the beginning all set up for them, and then they can start tweaking things and playing with it. And they would have to do it in 30 days because it's a 30-day trial. But when I opened it up, I was hugely impressed with how easy it was to use.
Easy to start and a long way.
Right.
A lot that you could grow in 30 days.
Exactly. And then obviously, like, once you've finished the simulation, then like all of a sudden you hit a wall in terms of like get it into Maya, render it out through one of those rendering programs. Like then it starts to become more complicated. But just there's an interactive scene where you can watch everything happen, and it's optimized specifically just for the simulation part.
It's simply true now that visual arts are a computer-intensive career. Is that right?
Coming from a supercomputer perspective, it's
really
not the hardest problem. It's certainly not a solved problem, but the biggest questions now are in real-time graphics and the sort of the rendering hardware. Like there was a time when I couldn't use a laptop to do that kind of thing, and now I'm using my laptop to do even like the really advanced software. So it's not necessarily quick, but it's not unusable. So it's getting better.
Well, actually, what I was asking is, do people who are fine arts majors these days, who would be painters and photographers,
you mean
should they feel a compulsion to be more and more computer savvy?
Absolutely, 100% yes. If an artist doesn't know how to program, they're at a disadvantage.
What did you study in college? CS?
Computer science.
Did
Yeah.
you minor, major, double major in something else like physics?
I did a study abroad for a semester at a film school,
Yeah.
but that was sort of my deviation. Yeah. I took like my whole senior year. I had a lot of AP credit coming in, so I didn't have to take gen eds, and so I spent my extra time here doing independent studies and things, and trying to find sort of the cross-discipline classes on campus. And there's like a video game design class, and I actually was working with groups at the NCSA before I graduated.
So talking to a student who wants to do what you do, you would tell them major in CS, don't major in art.
I would say at least take programming classes. Yeah, I don't. So my senior year, I took an informatics class, which was called Introduction to Programming, which was a little bit laughably easy for a CS major, but it was awesome in terms of how you learn programming. And I so wish that I had had it to learn programming in the first place. It was, you use Python, which is already a pretty user-friendly language, to create images. And all of the machine problems that we did were image-based. And so you could see a picture of your coding. And then you could say, oh, those pixels are wrong, let me change it, rather than having to look through just a big block of text and be like, oh, well, I printed out the wrong words or whatever. I feel like, so obviously I'm a visual person, right? So it makes sense that I would find that interesting. But I feel like even people who aren't necessarily the same kind of visual learner I am would have an advantage learning that way. So like, yeah, I would say like, especially artists, that's an awesome class for them to take.
But most of their faculty members are not ready to say you can specialize this way. not half the present graduate students in art are going to have an appetite or readiness to move in this direction. And I think they'll be protected by the art field for a long time. Hopefully, the other half will be supported also.
Mm-hmm.
But
It's
if you said yes 100% to your question of that's the future for the art,
For the fine art.
Fine
For
arts.
Visual arts, yeah.
in the academic sense, it's still controlled by departments and by faculty members who aren't ready for that.
Mm-hmm. And it's not that I think that like classic painting or classic sculpting is dead, but there are new techniques that are making what they do less unique. And so the fields where, you know, like where someone might be a successful painter for like just creating works of art for people's homes, now people can create digital art, which is just as beautiful to hang on a wall, that can be printed, like for a much lower cost and it's easier to distribute. So it's the industry is changing, and I think that the classic artistic media are becoming more exclusive. So it's not to say that like there aren't people in the arts that are going to be successful, but they're statistically you're much more likely to have success with digital tools.
What did you take in high school? What kind of?
You mean the CAD class that I was talking about? Yeah, so I took, I guess it was a full year of shoot, I don't even remember what it was called. CAD Key. It was a program called CAD Key. And we just, like, we spent the whole year modeling, you know, 3D sockets and gears and widgets and gizmos and stuff. And, you know, we were, the teacher would give us more and more complex models that we then had to recreate in the software. And then we spent the last 2 weeks of the semester using a plugin to CAD Key that did animation. And that was where I got started. It was those 2 weeks at the end of the semester where I was like, oh my God, it moves. So it was definitely, there was an epiphanic moment where you knew what was going on.
Thank you.
Thanks so much. You got to eat your pizza.
My pizza.